Quantum computers. You've heard the hype, right? They promise to solve problems we once thought were absolutely impossible. Total game changers for medicine, for science, for everything. But there's a catch. Lurking just beneath all that incredible power is a fundamental, almost fatal weakness. It's a paradox we have to solve if we're ever going to unlock that future.
And that right there, that's the billion-dollar question. The very thing that makes a quantum computer so powerful, its connection to the weirdness of quantum mechanics, also makes it incredibly fragile. It's like trying to build a skyscraper out of soap bubbles. So, how in the world do we fix that?
Well, to really get a handle on the ingenious solution, we first have to get up close and personal with the problem itself. And that problem lives at the very heart of the quantum world, the qubit.
Okay, so think about the bits inside your phone right now. They are rock solid. They're either a 0 or a 1, no in between. But a quantum bit, a qubit, it's a completely different beast. It exists in this delicate state called superposition, meaning it can be a 0, a 1, or somehow both at the exact same time. Now that's its superpower for sure, but it's also its Achilles heel. Because the slightest vibration, the tiniest change in temperature can just knock it right out of that state and bam, you've got an error.
So the first type of error is one we can kind of wrap our heads around. It's called a bit flip. It's exactly what it sounds like. A qubit that was supposed to be a 0 accidentally flips to a 1, or the other way around. It's a classic, straightforward corruption of the data. Simple enough, right?
But then you've got the phase flip. And this is a purely quantum kind of gremlin. It doesn't actually change the 0 to a 1. Instead, it messes with the special mathematical relationship between them. Think of it like an invisible error. You can't see it directly, but it corrupts the quantum calculation just as badly.
So you might be thinking, okay, why not just do what we do with normal computers? Just make a backup copy. Well, it turns out the universe has a very, very specific rule about that.
Yeah, because of the fundamental laws of quantum mechanics, you literally cannot create an exact copy of an unknown quantum state. It's a real thing. It's called the no-cloning theorem. And it means we can't just copy-paste our qubits for safety. Nope. We have to get much, much cleverer.
So if you can't clone a qubit, how on earth do you protect it? Well, the answer is just so elegant it's brilliant. You don't copy it, you use redundancy.
Here's the big idea. Instead of trying to make one single perfect qubit, we take one piece of information, we'll call it a logical qubit, and we spread its identity across 3 separate physical qubits. They basically become a team, all working together to protect a single message.
Now don't worry about all the crazy notation on the screen. The core idea is actually pretty simple. Our one logical qubit, the information we really care about, gets encoded across 3 physical qubits. They become entangled, which is a fancy way of saying their fates are now linked. They are forced to be in the same state. Either they are all 0s or they are all 1s together. So now if one of these physical qubits gets hit with an error and knocked off course, the other 2 still hold the original information. The majority rules and our data is safe.
Okay, that's cool. The information is protected. But how do we find the error without looking directly at the qubits? Because remember, the moment you measure a qubit, you destroy its special quantum state. It's a real catch-22.
We use something called a syndrome measurement. And this is the truly brilliant part. Instead of asking each qubit, hey, are you a 0 or a 1, which would break everything, we ask the group, hey, you guys, do you all agree with each other? This gives us information about whether an error happened without collapsing the delicate state we're trying so hard to protect.
Okay, so let's walk through it. Picture this. A random bit flip error hits one of our 3 qubits. We then perform these things called parity checks. That's our syndrome measurement. You can think of it as asking a couple of questions. We ask, does qubit 1 agree with qubit 0? And then does qubit 2 agree with qubit 0? The answers to those questions give us a unique signature, a syndrome, that tells us exactly which qubit is the odd one out. Once we know who the culprit is, we just apply a simple operation to flip it back. Problem solved. And check this out. This table is basically our decoder ring. It shows you just how powerful that signature is. If we get a syndrome of 0, 0, it means all clear, no error. But a result like 1, 0 instantly tells us, aha, the problem is with qubit 1. There's no guesswork. It's a perfect diagnostic tool for our quantum system.
So that handles the bit flip error, the one that's pretty easy to picture. But what about that other weird invisible one, that phase flip error? Can we actually fix that too?
Oh yes, we can. And the way we do it is just amazing. The phase flip code uses this clever quantum trick with something called a Hadamard gate. Think of it like putting on a special pair of glasses. To our naked eye, a phase error is totally invisible.
But when we apply this gate, it makes the phase error look exactly like a simple bit flip error. Once it's visible, we can use the exact same correction code we just learned to fix it. Then we just take the glasses off. It's a truly beautiful piece of quantum engineering.
And you know what? This isn't even the end of the story. These are just the basic building blocks. More advanced methods, like the famous Shor code, actually combine both of these techniques to create a system that can protect a qubit from any kind of single qubit error, whether it's a bit flip, a phase flip, or even a weird combination of both.
So, why does any of this matter? Because without this kind of robust error correction, a large-scale, useful quantum computer is, and I mean this literally, impossible. This quote right here gets straight to the heart of it. Every single company building quantum hardware today is in a race to implement these codes effectively, because without them, a quantum computer can't run any kind of long, complex calculation, like designing a new drug or breaking modern encryption, without errors just piling up and ruining the result. This stuff, this error correction, is the bridge from today's noisy, experimental devices to the truly fault-tolerant quantum computers that can actually change the world. And so, at the end of the day, the entire goal of all this complex, clever, mind-bending work is to do one thing: take hundreds, maybe even thousands of noisy, fragile physical qubits and engineer them into one single, perfect, fault-tolerant logical qubit. That is the real building block of the quantum future.
So we've seen how we can spot and fix errors that by all rights shouldn't even be fixable, basically by outsmarting the rules of quantum mechanics itself. It's an incredible achievement, but it really makes you wonder, doesn't it? What other secrets is the quantum world still hiding from us? And what other ingenious rules will we have to invent to finally unlock its full power?